So our next speaker is Vasileios Klimis from Queen Mary.
Oops, sorry.
Yeah.
Cool. Hello, everyone. Here I'm about to pitch an idea on validating weak memory persistency models. It's an idea which is adaptable to any architecture, any hardware, and we are considering here active model learning so that we can enhance the automation of the whole process, the validation process. Now, why bother with validation? There are mainly two big reasons for this. The first one is keeping vendors on their toes. We want to hold hardware vendors accountable by testing that the behaviors that we see are do conform with their specification. The implementation of their hardware do conform with the specification that they. And second, we want to make sure that the proposed semantics are sound, okay, are strong enough. We want models that do not rule out behaviors that can be observed in real life, and we want models also that do not allow, are not unduly, let's say, weak, so that they allow unicorns behaviors that can never be observed in real life. Now, it all started when we hit a wall, when we used a memory bus intercept method. We had purchased a device, a fancy device, which consists of a memory interposer, which sits between the motherboard and the memory module. And this way, it monitors all the memory access from the CPU to the memory. It intercepts these messages and log everything into an external device, the so-called DDR detective. And by inspecting this log, we should be able then to deduce the order in which this memory access, the writes, are committed to the persistency domain. Okay, the order, the persist order in this. Now, the problem with this approach here is that the observations here are post CPU. Okay, why this is a problem? Because it turns out in x86 architecture there is this pesky buffer here, the so-called WPQ, the write pending queue, which is a battery bucked buffer. And as such, it belongs to the persistent domain here, but it is inside the memory controller. And as I said earlier, we are, our observation point is post-CPU, which means that we don't have visibility of what is being persisted in this WPQ module. So our approach, this approach, the memory bus intercept approach, is not well suited for x86 architectures. While for ARM architectures, things are simpler. The persistent domain is just the main memory, the non-volatile memory. So we are nicely positions in this point here to monitor and observe everything that is being persisted. Nice. We have got some very interesting results with ARM, which we got a paper accepted at ICSC. Now, testing persistency is tricky, is definitely much trickier than testing consistency models. Traditional approaches that we know from validating consistency models fall short in our domain with persistency. Why is that? Because the programs cannot differentiate between volatile cache reads and those from the non-volatile memory. They cannot distinguish whether it's reading from a cache or from the non-volatile memory. So a write here could be chilling out in any of the caches or kicking back to the non-volatile memory with the program not being able to distinguish where each write is being located. Now, to crack this puzzle, memory hierarchy puzzle, we came up with a trick. Okay, it's a memory hierarchy timing attack. It's a simple idea. It's very straightforward idea. It's very similar to the echolocation that bats use to navigate. Okay, so the idea is that if I do a store, then, and I immediately fetch the same value, then I should be able, by timestamping all my instructions, to decide the location of my store. This sounds very simple, very trivial idea, but we have discussed this with Intel, and we believe that this is a viable solution. While it is a very simple, straightforward solution, the real magic with this approach is crafting a framework which will effortlessly, smoothly, automatically handles with the nitty-gritty of the memory hierarchy for any architecture, for every hardware. And then this approach would be pretty cool. So if this could be applied for any architecture in a black box, let's say, fashion. This is a closer look of where the stores, the persist could be, the writes to the stores could be located. So it could be, as I said, hanging out in any of the caches in the WPQ, if we have the x86 architectures, or the host non-volatile memory inside or it could be in any device memory external, if we have the CXL package connected to our system. As I said, what is really cool here is the crafting a framework that would automatically devise these patterns for any device, any architecture, any machine that will be connected. Now, to enhance the automation of the validation process, we are considering active model learning. Okay, and through this approach, we will be able to refine the model that we are after, that we want to validate, progressively in an iterative fashion, in a black box fashion. Okay, and I'm going to explain step by step how we're going to deal with this. Now, in this approach, machine learning, we have two main, if you want, two pillars. Okay, it's the learner, which is an algorithmic entity dedicated to information acquisition, and this is going to interact with a so-called oracle, or you might have heard a teacher. Okay, so no. The oracle is just a source of information with comprehensive knowledge about the target system. So basically, it's an abstraction of the target system, and in the context of black box approach that we are adopting here, it's the experiments itself, the oracle. Okay, this is the main idea. Now, to focus in and check out the details of how this how the learner engages with the oracle. I'm going to detail now step by step what's going on. So given that we have a persistency model, the one that we want to validate against the actual system, this model is posed to the oracle as an hypothesis model. Okay, and next, at the same time, the learner is posing through membership queries the inputs to this model and to the system, so that we can then scrutinize the system response according to this hypothesis. Then, so basically, these inputs are the test cases that we are going to work on. Then these test cases are used to simulate the hypothesis model, resulting in some prediction from the theoretical model. And we, at the same time, simultaneously, we execute these test cases to the actual machine, resulting to traces of behaviors. And then an equivalence validator will compare what the theoretical model predicts and what the traces of behaviors have been resulted from executing the test cases. In case of discrepancies, we should investigate carefully the reason for this. It could be a bug in the system, in which case we have to correct the bug, file a report. It could be a non-conformance with the specification, okay, in which case a revise of this specification would be necessary. Otherwise, we might need to refine the model so that we can align the predictions with the traces, okay? Because in this case, either the model over-predicted the result or under-predicted, in which case we need to refine it so that we can start then progressively with a refined version of this model, repeating the process iteratively until we reach into a satisfied, let's say, model. So this is mainly the idea of how we're going to refine a model, a prescribed model, a theoretical model, find discrepancies in this model, and not only find discrepancy, but refining this, improving this model into a better one. Now, machine learning here is quite handy, not only for refining the model, but it's also very handy for spotting patterns of timing variations that we discussed in the time stamping echolocation approach that we mentioned earlier. Okay, if we connect different architectures, different machines in our framework, then the machine learning will be able to spot patterns. Machine learning is good at spotting patterns of timing variations, so that we can imply deduce what the timing variations are, where the stores are located in caches and so on for each architecture. Also, the machine learning would be quite handy in spotting patterns. Yes, please. So, also another handy thing that we are going to, we will benefit from machine learning is spotting patterns, persistent ordering patterns. So, in case of litmus tests, there is a post condition that we have already to check what the values of the variables will be. And if you have a big, let's say, litmus test with a complicated post condition that you want to check, you might need the help of machine learning to spot the pattern, complex patterns of persistent orderings. Yes.
So from this, if you find that there is some mismatch, then also do you augment
there is some
mismatch between the specification and the test
okay,
cases?
Yeah.
Do you also generate new test cases from
yeah.
that?
From the counter examples that we get, then so generating test cases, it might be from the counter examples, it might be, we might use a repository, different repository with test cases. We might generate from the model using, for example, given an example that we could be, for example, alloy models. Alloy is good at generating instances that you can then transpile into test cases. And yeah.
Okay. Thank you.
Yeah, this is quite high level. There are a lot of to be explored.
I have a question about your echolocation. How precise are the measurements, and do you have any problems with noise, like in the sense that can you have a measurement overlap if it's in L1 or in L2?
We have done some tests, very trivial tests, and we have discussed with Intel that, and we believe that this is viable. I don't have much detail in terms of implementation to share with you now. This is very early days of this idea. But we have tried, we saw we can differentiate timing variations from caches and from non-volatile memory stores. We did distinguish a gap in timing variations here.
But if it's so difficult to know whether a write is coming from persistent memory or from your caches, how do you know the ground truth in that when you're doing those experiments? How do you know? How do you know this is right? This is a write coming from persistent memory, so that takes this. I'll measure that. And that takes this long. How long? Whereas this is a write coming from the L2 cache, and that takes this long.
Yeah, this is a job. Yeah, we believe that this is a job of machine learning. So if machine learning will just give us, let's say, a high-level figure of patterns. For example, in case we have 3 levels of cache L1, L2, L3, then in case the machine learning will return 3 patterns, 4 patterns of such, then we might easily
I see. So you see the writes either take this long or this long or this long, and you say, okay, well, that one's probably persistent memory, that one's probably L1, that one's probably L2.
Yeah.
Okay.
Yeah.
Cool. Couple of
Now,
minutes
in
left.
terms of, with regard to the formalism that we are going for the hypothesis model, there are different formalisms around to model concurrency, like the Petri nets, the process calculi, the actors models, and others. But the one that we are thinking seriously to incorporate in our approach is the concurrent clean algebra. It's quite elegant, and we think that it would be the best option to. So given this litmus test, this program, for example, you can easily, in this way, express in concurrent clean algebra this program. So the concurrent clean algebra introduces this operator, parallel operator here. So we have here a parallel composition of these 2 threads in this program here. Now the concurrent clean algebra expressions generate subclasses of POM set languages. A POM set is a partially ordered multi-set of events, okay, which nicely encapsulates an execution of the concurrent program. Now, to encode these concurrent clean algebra expressions, we think that POM set automata would be a nice formalism to incorporate into our approach. There is a lot to be explored about the subclasses of POM set automata and learning techniques for these subclasses that we are going to explore. As I said, we don't have much details in terms of implementation and that, but this is roughly high level what, and I would love to hear your feedback if. Yeah.
I'm a bit worried about the way you're measuring whether stores have made it to persistent memory, because you're measuring time. So that tells you what at best what the closest cache it's in is, but not how far it's made it. If I do a store and then I do a load immediately, I'd expect it to be satisfied by the L1 and get a fast round trip. But I don't know if it hasn't made it to the persistent memory, right? Because it's writing through. So how are you going to cope with that? Because the caches would be pointless if everything was evicted as soon as you did a load or a store.
Yeah. So we are expecting. We don't know. Okay, I don't know, but we are expecting that since, for example, in this case, we have, let's say, 3 levels of lines here. We're expecting that if the machine learning will come up, will return 3 patterns in this setup, then we will deduce immediately that the first one, the shortest one, is a store which is located in the cache. The other, the longer one is in here, and so on and so forth. So it will be empirically something that...
I guess the point is that you can't tell the difference between there being X in the cache or X in the cache and X in the host attached memory, right? You've shown it as 3 distinct categories, and you'd actually expect duplication because that's what the caches do, they duplicate.
Yeah. I don't know. We haven't thought about this. I don't know.
Final question from Paul.
Catch boxes. One thing you could do is have cross traffic that had some probability of ejecting it, and then it's still going to be ugly. But I've generated things like that, shown them to a hardware guy, and they've identified what CPU family it was. So natural neural nets handle it with care.
Thank you, Vasileios.
Thanks. Cheers.